So we've been talking about eigenvalues and eigenvectors, but what if we have a triangular matrix? How would we find the eigenvalues for a triangular matrix? Well, it turns out that the eigenvalues for a triangular matrix will actually just be the entries on its main diagonal. So let's look at this a little closer. Let's consider the matrix A equals negative 2, 3, 1, 0, 4, 3, and 0, 0, negative 2. So this is an upper triangular matrix. Here's our main diagonal, and we see we have non-zero entries in the top right hand corner, and we have zeros down below that main diagonal. So let's find the determinant of A minus lambda I. So we need to find the determinant of negative 2 minus lambda, 3, 1, 0, 4 minus lambda, 3, and 0, 0, negative 2 minus lambda. So we said before to find the determinant of a triangular matrix, it ends up being the entries down that main diagonal. We proved that back in chapter 3. So just in case you've forgotten that, suppose we were to write this out. I'm going to expand along that first column. So I have negative 2 minus lambda. And that's where that first row and first column cross. Times the negative 1 to the 1 plus 1. And I need to find the determinant of what's left over, which is 4 minus lambda, 3, 0, negative 2 minus lambda. And then we would have, moving down this first column, 0 times some stuff, which is 0, plus 0 times some stuff, which again would be 0. So now I have negative 2 minus lambda times negative 1 squared, which is a positive 1, times this determinant. And that determinant would be 4 minus lambda times negative 2 minus lambda minus 0 times 3, which is 0. So we would have this guy. This is our characteristic equation, and this is nice because it's already factored for us. That's why we like triangular matrices so much. They make it easy. And we always want to take that and set it equal to 0 to solve. So I'm going to put an arrow here that says the next step would be to take that and set it equal to 0. And when we do that, we would set each factor equal to 0. So we would get negative 2 as lambda, 4 as lambda, and a negative 2 again as lambda. That negative 2 has a multiplicity of 2. And you can see those are the entries down that main diagonal. So triangular matrices are nice because those values for the eigenvalues would be those entries down the main diagonal. So just for fun, let's find the eigenvectors. So for lambda is equal to 4, we're going to substitute this into A minus lambda I. So we're going to substitute into there. So negative 2 minus 4 is negative 6. 4 minus 4 is 0. Negative 2 minus 4 is negative 6. And remember, we want to solve A minus lambda I is equal to 0. So we're going to have zeros here. We're setting up a system, in other words. Plug everything in your calculator. If you want to do this by hand, you could. This one wouldn't be so bad. So I got 1, negative 1/2, 0, 0. 0, 0, 1, 0, and then zeros down the bottom. So this tells us x1 is equal to 1/2 x2. x2 therefore has to be a free variable. And then x3 has to be equal to 0. So our eigenvector, so we could think about this before I jump into the eigenvector this way. But we could use any number to substitute in for this. So if we wanted to use x2 as 1, then we could use 1/2, 1, and 0. A lot of times, though, you'll see that people don't like to use fractions when they talk about the eigenvectors or spanning sets. So what if we were to multiply this by 2? If we were to multiply this vector by 2, then we would get 1, 2, 0. So we can use that eigenvector. So now let's look at when lambda equals -2. If we were to plug in -2 back into this matrix, -2 minus -2 is 0. 4 minus -2 is 6. -2 minus -2 is 0. Again, we're solving a minus lambda I. Let's do RREF. And it looks like we're going to get that. All right, whoops, I made a mistake on this RREF. This is 1, 0, and then a 0, 1 here. So let's talk about what this means. This means x2 is 0 and x3 is 0. So x1 has to be a free variable. So then our eigenvector will be 1, 0, 0. So there are the two eigenvectors for the corresponding eigenvalues.